Hello everyone, welcome to another video, and in this one we are talking about Google's self-evaluation algorithm for deep research agents. So the idea is that we're gonna understand the self-evaluation algorithm which is proposed by Google in one of their research papers on deep research agents. So what has happened recently is that Google released a paper on deep research agent describing what the architecture of the research agent is, and in that paper they have talked about a self-evaluation algorithm which they have implemented within the agent to increase their performance, and we'll specifically talk about what that algorithm is and how you can implement that from scratch. So that is the overall agenda of this video, right? Now before going ahead into the self-evaluation algorithm, we should first understand what deep research agent is. So basically, if you have used language models like Gemini or OpenAI GPT models, there is an option to enable deep research. If you enable it, the model basically takes some time, does the entire planning of your question or whatever task you have given, then produce a detailed research report on this. And that's what deep research is. It's not similar to the basic or the general LLM call you do, and it takes some time. So what happens is that whenever you provide a topic to an LLM and ask them to perform a deep research, what do is they basically first create a plan. So there is a research plan for the particular topic which you have provided, and then the large language model goes topic by topic, or following the plan, it goes topic by topic which is mentioned in the plan, and it is try to perform a detailed research. While doing this research, it tries to go on to every topic, tries to go through the web, getting the recent information along with whatever information it already has, tries to point out the citations to which the information was retrieved from, right? A lot of things are done. It tries to understand what are the information which he has, which they have captured for the current research plan, whether there is any duplicates or not, whether there is any gaps or not. It tries to address those gaps as well. So a lot of complex process goes on into preparing this long form research reports through deep research agents, and that's what we are talking about. So how Google built this deep research agent, and what is the self-evaluation algorithm, what it is all about, and why they have used it, and why they have basically used it to increase the performance of their agent, right? So I'll go to the paper and I'll show the paper, but let's first discuss the self-evaluation algorithm very briefly. So this is how the self-evaluation algorithm looks like. What we have initially is 3 candidates. So what you can think of this as 3 candidates or 3 agents whose task is to perform a research on a particular topic. So what happens is that a single topic is given to these 3 candidates. So the topic is same, which is provided to these 3 candidates. The difference is all of these agents, C1, C2, C3, has a language model which they utilize to perform the search. Now the configuration of the language model is different for these 3 candidates. So they have a variation in the temperature and the top K values for the language model, and those values are set differently for these 3 candidates so that they can perform a diverse search, right? Once a candidate research a particular topic, it goes on through a series of iteration. So if C1 perform a research on a particular topic, then that is given to an environment, or basically you can think of a judge, which is probably judging the output of the candidate or the language model, and the environment or the environmental judge provides a feedback on the response. Now what happens is that if the output of the candidate C1 is C1, or maybe I can say the output of the candidate is C1 is O1, then a feedback is provided. Feedback F11 means feedback provided to candidate 1 on its first output or first iteration, right? So this is the feedback is provided, and what happens is that again the language model, or basically the candidate or the agent, tries to incorporate the feedback, or basically tries to understand the feedback, and it tries to refine the output. Now you can think of this candidate is again refining the output, and you can think of this as again O1 or O-1, right? So O-1 is nothing but the feedback, or basically the output which is returned by the agent after incorporating the first feedback. After that, what happens is that the same cycle is performed where this output is provided to the environment, and the environment again provides their feedback. Now this feedback is termed as F12, which is basically feedback provided to the first candidate on the second refinement. Now what happens is that the same cycle is performed, the candidate sees the feedback and it tries to incorporate this feedback, and then again returns the third output. That is, after incorporating the second feedback from the environment, it is trying to produce the third output. Now again, I can change this and I can call it O_1, saying that this is the feedback after, or basically this is the output after incorporating the third feedback of the environment. And again, this cycle can continue. So it can again get some feedback from the environment, and then it have to incorporate that feedback and it has to produce the output again. Now this is a similar cycle, and this can go on. So when you're constructing the algorithm, you have the control on how many iteration of environment feedback you want, right? So suppose in this image, I am showing that I want 3 iterations of environment feedback and I want to incorporate it in the output, and after that I want to return the final result. So this is a cycle of environment feedback, or basically it is a sequential cycle of refinement where the language model or the agent C1 gets a research topic, it performs its research, whatever research was performed, it was given to the environment, and environment provide a feedback on the research that if there is any gap on this, or there is any duplicacy, or if the candidate missed adding some important point, those feedbacks are provided, and then that candidate incorporates that feedback and tries to refine the response, or basically tries to improve the quality of the response. And then again, the output which is produced is again given to the environment and a feedback is provided, and this cycle goes on. And when you are constructing the algorithm, you have the total control on how much cycle of environment feedback you want to get, right? And after that, once your cycle is exhausted, the final output after incorporating all the feedbacks from the environment is returned for a crossover. Now the idea is this particular operation which I mentioned happens for 3 candidates, or like for in this algorithm I have taken 3 candidates, but you can take any number of initial candidates. Maybe you can take 5 to 6 initial candidates with different model configuration that goes through the same cycle of environment feedback or sequential refinement, and after that all these produces the final output, which is crossover, or crossover meaning which is basically merged. So what happens is that the same cycle of environment feedback happens for all the candidate, and this happens in parallel. So what you can do is that you can like do all these operations parallelly, because these 3 are independent, they are not dependent on each other. So the sequential refinement of the output of each candidate can happen parallelly, and after that, once all 3 is done, you can merge the final output and you can perform a crossover. So what happens in crossover is that there is a final agent which is waiting for the outputs from the candidate. After the environment feedbacks, the output is returned, and that agent sees all the outputs from the different candidates, and it tries to incorporate. Basically, it tries to take all the important information, if there is any, from all the different candidates, and it tries to bring a single output. So basically, if there is one critical piece of information present in one of the candidate which is missing in multiple other candidates, then that will be incorporated in the final output in order to increase the quality. And in this way, the final output which is built is returned by the crossover candidate after performing the crossover. And now this is the self-evolution algorithm which Google is talking about in their deep research agent paper. Okay, so now let's talk about the paper, or let's actually see this paper. This is the paper which I'm talking about. This is by Google, titled Deep Researcher with Test Time Diffusion. So the name of their deep researcher is Test Time Diffusion. The idea is that they basically refine the report in a sequential manner, and they take inspiration from the diffusion process in order to refine their research report iteratively. Now I'll not go into the deep researcher architecture, that is probably out of scope for this video, but I'll probably go into the algorithm, the self-evolution algorithm which they have introduced, and they have introduced it in almost all of these components. So this is kind of a modular algorithm which you can inject in most of the components of the deep researcher to enhance their performance, right? So this is basically the introduction and all. There they also mention the current architecture. They have compared multiple other deep researchers from other orgs as well, discussing their architecture and how their architecture is different from it. Apart from that, if you will go on page 5, this is the component-wise self-evaluation algorithm which I was talking about, right? If I'll zoom it here, this is the diagram, or this is the actual self-evaluation algorithm, which is very similar to what we have seen earlier. The only difference is here is an environment which provides the feedback, and this is the initial candidate. So similarly in our previous, as we saw previously we have 3 candidates. Similarly here as well, they have taken 3 candidates for the example, or basically they have taken k candidates. K can be any arbitrary number. You can set it the way you want in your algorithm. Every candidate produces some output which is given to the environment, and then the environment provides the feedback. The feedback is incorporated and another revision output is performed. So revision is basically when the candidate gets the environment feedback, takes it in, analyze it, and then produces the output on top of it. That is the revision. It is again passed to the environment feedback. The same process happens, the feedback is incorporated, and then another revision or another output is produced by the candidate, which is being said A2. And in same way, this process happens for t times. Again, if you are running your own algorithm, or if you're building your own version of self-evaluation algorithm, you can set the value of t. T can be any arbitrary number, right? T here means the number of iterations of environment feedback happens on your candidate output. After that, you get a final output AT, which is given to the final answer after the crossover. Now, here 3 candidates, all these operations are happening parallelly for all these 3 candidates, and their output after performing T set of environment feedbacks, these corresponding outputs are going into the crossover algorithm. And as I mentioned earlier, once the crossover happens, the final answer is returned, right? This is the overall idea, and this is what they are talking about as well. If you'll see, they have clearly mentioned about the first point, which is the initial states. This is the initial state here. The leftmost block produce multiple diverse variants of output conditioned on output of previous stages. Each block is implemented with a unit LLM agent, allowing for sampling of multiple answers using varied parameters to explore a large search space. This ideally leads to discovery of potentially more valuable information. Now, the idea is we could have provided the same language model to these 3 candidates. If we don't change the configuration of the model will probably work in a similar way in all these 3 candidates and will not achieve much, even though we take multiple candidates. They will eventually produce similar response, get similar feedback, and perform similar refinement. In order to resolve that, what the paper has done, or what paper is mentioning, is that they are providing the large language model or an LLM agent to the candidate, but they have varied the parameters of the model given to each candidate. So they have made some changes in the temperature, in the top K parameter, and some other parameters as well, through which the model can produce or basically search on different spaces, or the model can behave differently. So each model provided to the candidates behave a bit differently and produce a different set of output, letting them to search a huge space. Since these candidates are working in parallel and produces different set of outputs, when the crossover happens, the different set of information from different candidate outputs are merged and a high quality output is produced. That is the overall idea. Environment feedback. Each answer variant is assessed by an LLM-as-a-judge, utilizing the auto raters for metrics such as helpfulness and comprehensiveness. These raters not only provide fitness score but also generate textual critique that help improve the answer. This is similar to what we talked. We have an environment which provides feedback. Now in this paper, they are saying that the environment is nothing but another LLM which is acting as a judge. So there is another large language model which is acting as a judge who takes the output of the candidate, tries to provide feedback on those output based on how helpful or how comprehensive the output of those candidates are. Right? And now the environment or the LLM as a judge does not only produce a fitness score, basically how fit your output is, but along with that, it also produces critique, basically how you can improve the output in a text manner. so that that particular critique or feedback can be incorporated by the candidate to produce a revision or a refinement. That's what they are talking about here. That is a revision step. With the scores and feedback from the previous step, each variant undergoes a revision step to adopt towards better fitness score. The environmental feedback and revision steps repeat until a stopping criterion is met, forming a loop workflow. Now this particular set of revision happens in a loop. That's what we are talking about. This is a loop, which currently this is happening t times, but you can decide what the value of t can be, right? As we talked, the revision step is nothing but the environmental feedback received from the environment or the LLM as a judge is incorporated by the candidate, and the operation or the output is basically improved, right? Doing this in a loop. The last thing is crossover, which we also talked about. Finally, multiple revised variants are merged into a single high quality output. The merging process consolidates the best information from all the evolutionary paths, producing superior context for the main report generation process, right? As I mentioned, what happens is that the candidates provide output after the environmental feedback. Those output are consolidated, and the best information or the important information from those outputs are consolidated, and then it is being used to produce one high quality output. And since the models provided to the candidate have different configuration, they go on to a different set of evolutionary paths, meaning they produces different output, they get different set of environment feedback, and this process of evolution or this process of evolution path is different for different candidate, and that's why they produce different set of outputs which are high quality and can be merged to produce a single set of even high quality output. And that's what the crossover is. And this in total is the self-evolution algorithm which we are talking about. Now this is the theory part. This is how the self-evolution algorithm looks like in the paper. Now as a next step, what we'll do is that we'll try to implement it from scratch. So let's move on to the code part where we're gonna actually implement the self-evolution algorithm from scratch. Now this is the AI Engineering 101 repo. The link to the repo is already, or basically the GitHub link to this repo is in the video description, so you can check this out. And if you're following, this is basically an AI Engineering 101 series which I have started long back. What I basically do is that I try to tackle multiple concepts and problems and projects related to AI engineering, and we try to implement it from scratch in these set of videos. So you can check out the previous videos if you want to learn more about AI engineering, right? Now this is the implementation of the self-evolution algorithm. I'll quickly collapse this. So this is the entire notebook which implements the self-evolution algorithm. What I'll do is that I'll try to basically first frame the problem, what we are trying to solve. Okay. So what we are building here is that we are building an agent which can answer your question, and we are implementing the self-evolution algorithm. So initially what you have done is that if I give you a question, you can give it to the language model. The language model can provide the answer, and then you can return the answer or you can print the answer. That is simple. It's basically a language model call. But what happens is that if a topic which I gave you is very complex and it requires some results, like it requires a web search because there might be some recent research on that particular topic which is out of the context, or basically which is beyond the cutoff period of the language model. So a language model might need a web search for that topic to get more information from the web, incorporate that and give you the answer. Now if you try to do it in one go, it can be the chance that the web search returns a response which is huge, maybe 20-30 pages or maybe 100,000 pages, and the language model might not be able to incorporate the entire response in one go. So you can introduce this self-evolution algorithm which will try to perform the set of refinement. So what will happen is that you do a web search, you get the output for the particular topic, you give it to the model, get an output, and then you start the set of environmental feedback where an LLM as a judge sees the output of the candidate, gets the web search result, and try to understand that if the output is up to date with the web search result, or if the language model has missed some of the outputs from the web search or some of the results from the web search into the answer, or they have added some duplicates, or there is some infeasible part in the answers. So all of these are trying to be removed through the environmental feedback and refinement. And after that, we perform the crossover. That's what we'll do. So this is a query. What are the investment philosophy of Duane Yongpin, Warren Buffett, and Charlie Munger? So this is one of the research query. And what we'll do is that we'll provide this query to the self-evaluation algorithm, and we'll try to see how they try to tackle this, right? Now, how you will basically implement the self-evaluation algorithm. As I mentioned earlier, the first thing you have to do is that you have to initialize the set of candidates which will go on through the environmental feedback iterations, right? So if you'll see the perform self-evaluation method, this is how the method looks like. What I'm doing is that I have a set of candidates, or basically a set of candidate configuration. As I mentioned, as it was mentioned in the paper as well, different candidates are provided with a unit language, large language model with different set of configurations. That's what I have done here. Every candidate has a different set of configurations. I'll show you what the configuration looks like. And what I'm doing is that I am iterating on these candidates. So for this tutorial, there are 3 candidates which I have taken. Now I am iterating on the candidate one by one. Every candidate is given a unit language model. The catch is the temperature and the top K parameter is tuned according to the candidate configuration. And every candidate config has different values of temperature and top K in order to search a diverse space. You can experiment with it and maybe add more parameters, provide different set of values to more parameters and see how the language model performs. It's all in the research, right? You have to do multiple set of iterations, a lot of research to understand how it goes. Once we have the model, we perform the self-evaluation. And then after the self-evaluation, we get an evolved answer, and this evolved answer is appended to the set of answers, and then the crossover is done. Now, the idea is the evolved answer is basically an array, a list of array, and every candidate will have a set of evolved answers, right? Once the evolution start, in this method, the environmental refinement happen, and after all the set of environment refinement, the answer, which we called an evolved answer because it has gone through the environment feedback, this evolved answer is added to the evolved answers array. Now this array is nothing but it holds the evolved answer of all the candidates. So currently I have 3 candidates. All these 3 candidates will go on through the environmental evolution or environmental refinement process. The final answer will be provided, and all these final evolved answers will be kept in a set. Now this set will be given for the crossover, because in the crossover what happens is that final evolved answers of all the candidates are given and merged. So this is what happens here. This candidate crossover method will merge all the evolved answer, and it will also have the idea of the search query so that it can perform efficient merging of the answer, and then the final answer will be returned. And that is what a crossover evolved answer is. After the self-evaluation algorithm completes, this is what we get. Now this is the perform self-evaluation algorithm. Now this has multiple steps which I haven't gone through. So let's go on to that. First is the candidate configuration, how it looks like. So this is the candidate configuration. We currently have 3 candidates, and every candidate have different configuration. So for the first candidate, we have top K value of 30, temperature of 0.5. For the second candidate, we have top K value of 40 and temperature 1. And for the third one, we have top K value of 50 and temperature 1.5. Now these are the set of configurations provided to the 3 candidates, right? And once we perform the looping, we provide these configuration individually to the individual candidates. After that, what will happen is that the self-evaluation loop or the environment refinement loop will start. This is implemented in the start self-evaluation. So let's go on to this method. This is the method start self-evaluation. Currently, as I mentioned earlier, if you are building your algorithm, you have the total control on how many set of refinements you want. In the paper, remember, this was denoted by the term T, which gives the number of refinement loops. For us, this is max refinements. In this algorithm, we have set the value to 3. You can increase the value and see how the output looks like. But for the sake of this video, the value is 3, meaning the output will go on to 3 set of environmental refinements, and after that the final output will be provided. Now this is sequential. So you have to wait for the model to answer and then get the feedback and then provide another set of refinement and then again perform another set of refinement. We have a refinement count that takes into the account how many refinement has happened, and it makes sure that it is less than the max refinement. So there is a while loop here. This is the answer, this is the environment feedback, and this is the web results. So web results is nothing but we perform a web search. Web search method is nothing but it takes the search query, performs a web search and returns the web results, and it is saved here in the web results response. Now what can happen is that this web results is provided while generating the answer. Initially the environment feedback is empty. So what happens is that in the first step, once the generate answer method is called, we provide search query the web results as well. These two will be there, but the environment feedback will be empty because this is for the first time. So for the first time, the model will not get any environment feedback. It will only get the query, the search query and the web results for that search along with the model. It is important to pass the model because this model is uniquely set up for this particular candidate with a different set of configuration. So we'll make sure that we'll use that particular model, right, for generating the answer. Now the candidate goes on and generate the answer for the query and the web results, and the answer is present here. Now we can see the generate answer method here. This is a simple LLM call with a particular prompt saying generate the given the search query, web results and the environment feedback, provide a concise and accurate answer. We have passed the search query, the web results and environment feedback. There is a small note that if environment feedback is provided, incorporate into the answer, right? So initially what will happen is that the environment feedback will be empty. So the language model will not take this environment feedback in picture, but for the rest of the refinement sets, there will be an environment feedback and it will try to incorporate it for answering, right? So that is the overall idea. So this will gonna go ahead and it will generate the answer. Now let's move back. Now once it has generated the answer, it will try to get the environment feedback or basically the environmental feedback on the answer. And what will happen is that you can get the environment feedback and you can get it here, and then you can get it, basically you can get the environment feedback. So get environment feedback is simple. The answer which is produced by the candidate and the search query along with the web results is provided to the method, and this method has an LLM as a judge which sees the answer and the web results and try to point out what the feedback is, and then this feedback is given back. So initially the feedback was empty, but now this environment feedback will hold the feedback from the first iteration and will be given back to the generate answer when it is searching for, when it is provided the search query and the web result. That environment feedback will be provided so that it does not make that mistake and it try to generate a better answer, right? And we increment the refinement count by 1. Now environment feedback method is also very similar. There is an LLM as a judge which has been provided with this prompt. Given the answer, search query and the web results, provide feedback on the answer provided for the search query. Keep the feedback concise and focus on factual accuracy. Now this is the answer, this is the search query and this is the web result. Now the model will try to provide a feedback to it. Now you'll see that we are not using the same model as the candidate because the environment is a separate LLM as a judge and it has its own model. So we don't need to pass the same model which the candidate is using because it has a different set of configuration. So for this, I am using a Flash model with a default set of configuration. I'm not making any change into it and I'm letting it provide the feedback on the provided answer. And then the feedback is returned. Let's go back to the method. Okay, so once the environment feedback is received, it will try to perform another set where this environment feedback is given to the model while generating the answer, and then it tries to produce or return a better answer by taking that environment feedback into account, right? And in this way, we can keep doing it until the max refinement loop or the number of max refinements is exhausted, and this will run for 3 times. We'll get 3 environment feedbacks, we'll incorporate it and we'll get a better answer, and after that the final answer after incorporating all the feedback is returned. So this is the start self-evolution. Now moving back to the method, this is the method. We got the self-evaluation, we did the self-evaluation, we talked about this method, we got the evolved answer, and we added the evolved answer into the set of all the answers. Now this happens for all the candidates, and then we perform a candidate crossover. Now candidate crossover is very easy. What is happening is that all the answer which we have received after the environmental feedback from different set of candidates, all of these answers are provided to the model along with the search query, and candidate crossover tries to merge it with a common answer. Now I have used the same prompt which is used in the Gemini, or basically in the Google test time diffusion paper. This is the same prompt which they have used. Your task is to research a topic and try to fulfill the user query in the user tags. The instruction is you are given a list of candidate answer in the answer list tag below. Combine them into a single answer so that it best fulfills the initial user query in the user tag. If there are conflicting information, try to reconcile them into a logically sound way. Now we provide the search query here, we provided the answer list here, and the candidate crossover algorithm tries to merge it into a single better quality answer, and that is finally returned here. This is the candidate crossover algorithm, and this is it. This is the candidate crossover algorithm which returns the which cross over all the answer and tries to return the final better answer. And this is how you can implement the self-evaluation algorithm. I'm sorry, this is the method. Yeah, this is the self-evaluation algorithm. Now you will see an interesting thing is that here in this algorithm, I am doing this sequentially, but in the paper, we saw that this particular algorithm was implemented parallelly. So there were 3 candidates, then 3 candidates should go in parallel and should return the final answer parallelly, or basically should return the final refined answers parallelly, and then the crossover should happen. But here what is happening is that we are waiting for the first candidate to be done, then we are starting the second candidate, and then the third. Now this is time taking because this is happening sequentially. So I have written another set of same method which utilizes same modules but in a parallel way, so that you can basically leverage the cores of your CPU, try to run 3 threads in a parallel fashion, which will gonna be responsible for the environmental refinement of 3 candidates in parallel. And after that, all of the 3 are done, will gonna run the crossover algorithm which will gonna merge them, and we'll see that running the parallel algorithm is better, or is basically faster as compared to the sequential one. This is the algorithm. I can also talk about the web search. So web search is nothing but we perform, here I am using Tably search. Tably is also one of the company which provides search as a tool to the large language model. So you can basically provide this search as a tool which your language model or basically your agent can use at will. But here I am just using it at will, providing the search query along with the number of results I want, and I'm getting the result, and then I'm parsing the web result in the form I want, and then I'm returning it so that the large language model can use it. So that is the basic idea. And after that, this algorithm, this self-evaluation algorithm runs, and it returns the final answer. So I can basically run this one as well, and going forward we're gonna run this and we'll see what happens. So now let's run this algorithm and see what happens. So if I run this, load.environment is not defined. Oh, I basically have to first run all these methods so that it is there in the memory so that it can be referenced later. So I'll run all these methods one by one, and after that I can finally run this one. So the first candidate will be spawned, it will perform the web search, refinement iteration 1 will happen, it will get the environment feedback, and then it will gonna perform another set of refinement. So in the first refinement, it is generating the answer, then it is generating the environment feedback for that particular answer, and then we'll perform another set of refinement where this environment feedback is incorporated to get a better answer. Now this will run for some time, and after that we'll see how it runs and the total time taken for the execution. Okay, so now I am done with this. It basically took 3 minutes 7 seconds. It first spawned the first candidate, performed the web search, first iteration done, got the environment feedback, second iteration done, third iteration done. Then it spawned the second candidate, happened the same. The 3 iterations went for the second candidate. Then it spawned the third candidate. The 3 iterations went for that. Then it finally evolved. It basically performed the crossover of the candidates, of the 3 candidates, after the environment feedback was incorporated. Then the final answer is here. So the final evolved answer after crossover is something like that. So it's a pretty big paragraph where it is specifically telling the investment philosophy of Duan Yong, Ben, Warren Buffett, and Charlie Munger individually. It has taken the web search results into account while answering this. Now this is good. This is how you can basically implement a self-evaluation algorithm in your workflow. Now I'll try to make it a bit better, because this was a serial flavor of this algorithm where I was executing candidate in a serial fashion, one after the other, but that is not the preferred way. We should ideally execute it in parallel so that we can save some time. The serial execution takes around 3 minutes 7 seconds. Now what I'll do is that I'll try to execute it in parallel. This is how the parallel flavor of the self-evaluation algorithm looks like. We have a thread pool executor where we are providing 3 workers, basically because we have 3 candidates, and these 3 workers will take each candidate and will run these candidates in parallel. So the environmental refinement, the sequential environmental refinement for these 3 candidates will now happen parallelly by these 3 workers. And the idea of the parallel flow, or basically of async execution, is that we don't get the, or basically we don't halt the loop for a particular method to complete. We basically say that, okay, let's execute this method and let's wait for this response, or basically let's take the future, or let's take the promise of the response and store it, and let's keep the workflow executing. We don't have to wait for it. Whatever blocking or whatever thing which you need to do, or basically whatever thing which is being blocked by this operation, happens after the future response is received. So the idea is that these 3 candidates can run in parallel, but the crossover needs to happen after all these 3 candidates run. So we don't need to wait for one candidate to run after the other. These 3 candidates can run in parallel. That's why they are running in the thread executor. And the response, so once the self-evaluation start, the response is saved in the future. So it is not getting the exact response. It is just keeping the future of this particular method. So even though this method is running, it is stored in the future response, or the reference is stored in the future response that will be updated once this method is complete, right? So you can, if you want to know that whether the method is completed, you can call the result method and it will gonna return the data when this method completes. Now the blocking flow is the candidate crossover. So we just need to wait for these 3 candidates to run in parallel, and after that we can call the future.result to get the evolved answer. So this way what happens is that the blocking flow, which is the candidate crossover, will only be there waiting for the output, but all the 3 candidates, this will run in parallel and they don't have to wait one for the other. And that's why when I'll run this, you will see the logs will not be in a sequential ordered fashion the way it was here, like candidate 1, candidate 2, candidate 3. It will not be in that fashion because these 3 candidates will run in parallel together. So we'll see the logs will be in a very random order here and there. So you're probably not able to understand when you'll see the log what is happening, but things will go well, and after that you will see the crossover of candidates happening. So performing crossover of candidates will always happen after all these candidates have executed, but this will execute in parallel. So I can run this one and you'll see what happens. Okay, so if I run this, this method is basically, okay, I have defined the self-evaluation method. Now I'll run this. So I can probably clean this one. Cool. Now what I can use is that instead of perform self-evaluation, I can perform self-evaluation in parallel, and I can run this. So this will execute the candidates in parallel. Now you'll see the candidates, the logs are totally here and there. We spawned all these 3 candidates at once parallelly, and they are going the environmental refinement flow parallelly. So that's why this log is pretty disordered here and there. first iteration for all the 3 candidates happened. They all got the feedback. Then second iteration for all these candidates happened. One got the feedback, one is generating the answer, and this will go on, and then we'll probably go to the third candidate. Okay, so basically all the candidates are working in together, and all of them got the environment feedback, generated the answer. So basically this will happen for 3 times. So by seeing the logs, it's difficult to say which candidate is being executed until and unless we mention that specifically in the logs, but this will go on for some time. But I can confidently say that this will take less time than the sequential flow, which ran for approximately 3 minutes 7 seconds. And now, okay, we have the answer here. So you'll see the logs are pretty distorted, but once all these candidates were done, the blocking flow, which is performing crossover of candidates, happened at last, and we got the final response. This is how it looks like. It is similar to what we got in the sequential flow, but if you'll see the time, the parallel workflow took less time. It took around 1 minute 8 seconds. So basically the sequential flow took 3 minutes 7 seconds. It took 1 minute 8 seconds. So sequential flow took 3 times the time taken by the parallel flow, and this makes sense because we were running 3 candidates in sequential manner. That's why it took 1 minute for each candidate. So 1 minute, 1 minute, 1 minute, around 3 minutes. But in parallel, these 3 candidates ran together. That's why one candidate took 1 minute. So all these 3 candidates run parallelly, and they took a minute to execute. So the calculation works in the favor. And this is how you can basically implement the self-evaluation algorithm in parallel, and you can get a decent response from it. Now, there are a lot of different benchmarks which lets you judge how concise or how helpful or how insightful the output of your research task is. So basically if you want to judge whether including the self-evaluation algorithm in your workflow let you get better answers, then maybe you can use those benchmarks to judge or basically to provide a score to your research answers, and you can have an idea whether self-evaluation algorithm is working for you or not. And yeah, that is the overall implementation of the algorithm. So that was it in the self-evaluation algorithm. The interesting thing to notice, if you have watched this video carefully, you will see a particular instance where I have not provided the actual answer in the environment feedback during the revision. So if you don't remember, you can go back where I am implementing it in the code, and if you'll see the particular self-evaluation algorithm where a single candidate is going through the environmental feedback loop, you'll see that I'm only providing the feedback along with the web search result and the search query. I'm not providing the answer which was initially generated by the language model. The only thing language model gets is the question, the web search result, and the feedback, so that it knows what not to do incorrectly and it will take care of it. Now, as an exercise, what you can do is that when you are implementing your own version of self-evaluation algorithm, you can go ahead and give the answer as well. So along with providing the environment feedback, the search query, and the web search result, you can also say that, hey, this is the initial answer which was provided by the model. Here is the environment feedback which has been received on this particular answer, and all of this thing is for this particular search query. So try to incorporate this feedback into this answer and try to produce a better set or better version of answer by looking at the query, the web search result, the initial answer, and the feedback. And then you can try to see whether your self-evaluation algorithm is working even better or not. So this is a set of exercise which I'm leaving for you folks, which you can do when you're implementing it. Now, this was it. The source code for this particular code walkthrough on self-evaluation algorithm, you can get that. The link to the source code is in the description of the video. As usual, it is the part of the AI engineering repo. So if you click on the link, you'll directly go to the source code, which is a part of AI engineering 101 repo on GitHub. And this is the paper. The link to this paper, I'll mention that in the link. No, sorry, in the description of the video. You can get that this paper from there as well. And yeah, I'll meet you in the next video.